What's up? I'm Vin, and today I want to go through the Algebra 2 June 2023 Regents, and I'm going to do parts 2, 3, and 4, and I'll leave a link to a copy of this test in the description below. Now let's get started. So first we're going to be doing the part 2 questions, and each question here is worth 2 credits. Question 25, we have the business office of a local college wishes to determine the methods of payment that will be used by students when buying books at the beginning of the semester, and we have to explain how the office can gather an appropriate sample that minimizes bias. So the idea for this question, when you want to minimize bias, you should be thinking about making the survey as random as possible. So then there's a few ways that you could get full credit here. You could say survey every 5th kid that enters the campus on a day where the campus is busy. But looking at a few of the full credit responses that were in the model response set, my favorite way to answer this is to just simply pick random names from a list of the students that attend the college. So pick random names from the list and just ask them, how will you pay? Question 26, we have to solve this equation algebraically. If we just use the calculator here, we're going to get 1 out of 2, but if we want the full credit, we have to be able to do the algebra. So we have this equation, and the first thing that I notice is we have a square root, and the opposite of taking the square root is to square something. So we're going to square both sides like this. So on the left side, the square root and square cancel, leaving us with just 3x plus 7. And now on the right side, be careful. Don't do something like this. Don't say x squared plus 1. Okay, this is a very, very, very common bear trap, all right? I've seen students do this in Algebra 1, Algebra 2, even all the way up to calculus. You have to be very careful with this. Make sure that you're doing x minus 1 times x minus 1, because if you don't do this and just do that x squared plus 1, you're ignoring the outside term here and the inside term when you distribute. So we have to make sure we do this correctly. We have x times x is x squared. Then we have x times negative 1 is negative x. We distribute the negative 1, we have another negative x, and then we have negative 1 times negative 1 is positive 1. And we just bring down this 3x plus 7. So now we combine like terms here, so we're going to have x squared minus 2x, and then plus 1. And now from this step, we have a quadratic equation, but we need to get everything on one side. So I'm going to move this stuff to the right. I'm going to do minus 3x on both sides. And in one step here, we could do minus 7 like this. Okay, so you can do more than one step of algebra in one line here. So we have 3x minus 3x canceling and 7 minus 7, leaving us with just 0. And now we have x squared minus 2x minus 3x makes minus 5x. And then we have 1 minus 7 is minus 6. So now we have to think here, what are two numbers that have a sum of negative 5, and the numbers also have to have a product of negative 6. So if we think about it carefully here, the two numbers that work, we're going to have x minus 6 and x plus 1. And I know these numbers are good because negative 6 plus 1 is negative 5. And if we multiply negative 6 and 1, we get negative 6. So now we find the roots here. So we're going to set x minus 6 equal to 0, and we're going to set x plus 1 equal to 0. And if we solve this equation, we get x equals 6. And if we solve this equation, we have x equals negative 1. So we have two solutions. But no, this is another dangerous bear trap here, okay? We have to be very careful. You have to actually check to see if these solutions work. So now we investigate here. We have when x equals 6, we plug into the original equation here, and we're going to have 3 times 6 plus 7. And we're setting this equal to 6 minus 1. And let's see if this works out. So that's going to give us 18 plus 7, which is 25. And now we have the square root of 25 equals 5. 5 equals 5, so this checks out. So x equals 6 is definitely a solution. But now let's see what happens when we plug in x equals negative 1. So for x equals negative 1, now we have, let's see, 3 times negative 1 plus 7. Is that equal to negative 1 minus 1? And this is going to give us here, we're going to have the square root of 4 is equal to negative 2. But 2 is not equal to negative 2. Okay, this is not true. Okay, so this is not true, which tells us here that we have to reject. Okay, so we're going to reject this solution here. We only have one answer, x equals 6. Question 27, we have this function p of t modeling population of bacteria, and we have to determine whether the population is increasing or decreasing over time, and we have to explain our reasoning. So the population, once again, is modeled by p of t. So what we're really trying to find here is p of t increasing or decreasing. So what I'm thinking about here, p of t is an exponential function. And I know this because we have a number being raised to a variable power. And anytime you have exponential growth and your function is increasing, that's when you have something like a to the t and the base a is greater than 1. And if you want your function to be decreasing, when you want something like exponential decay, you're going to have a to the t power, but in this case, the base a is going to be between 0 and 1. So we have to determine the value of a here, or that's one approach. And to me, it's the most reliable because it's backed up by theory, that we just have to determine the value of the base. So then the next thing that I'm thinking about here is the law of exponents. When we have a to the b to the c power, that this is equal to a to the b times c. So what I'm going to do is I'm going to use this rule, but backwards. I'm going to rewrite p of t. P of t I'm going to say is 37 times, and instead of writing e to the single power, I'm going to call this, I'm going to have it as e to the power 0.0532, and this I'm raising to the t power, because once again, if I want to bring it back to the original, I just have to multiply these two when I go right back. So now the $1,000,000 question is, what is the value of this base here? So now we could type in this entire expression here. We're going to have second ln, that's going to pull up e to the x, and now in the exponent spot, we have 0.0532 like this. And notice here that this base is a value greater than 1. And what I said before is that if our base of our exponent is greater than 1, that would make our function increase. That's exponential growth. But another thing I could do here, this is an alternate method to solve this, is we could just type in the original function like this. So that's 37e to the power 0.0532. And then I tack on the variable here like this. And now when we press graph, notice we don't see anything. And if we press second graph, notice the table starts at 37 and it starts to go up. So I would have to go to the window setting here and make the y maximum. Let's say I make it 100. And now I press graph. And you see how now we could see that this is exponential growth. So you could, if you wanted to, just type this in the calculator and say the graph of p of t is increasing over time. As t increases, p of t goes up. So that's something like, that's an alternate way of doing it. But me personally, I like using this because it's more technical. It's using facts, and this is backed up by theory that a to the t is an increasing function when the base is greater than 1. So I personally like that explanation more. But once again, you could use whichever one you like the most. So now we'll just plug this in here. We have p of t now is equal to, we have 37, and I'll write out a few decimal places. We have 1.054640552. So I'll write out the entire thing like this. So this is p of t expressed with an actual value. And now think about what we said before, that the base of this exponential function is greater than 1. So p of t is increasing over time. Now, one small detail, I mentioned the coefficient of 37 just to be a little extra technical here, because if we had a negative 37 in front, then that would reflect this graph over the x-axis, and this would just keep decreasing. But since we're in a real-world context here where we're talking about the population of bacteria, it's kind of implied, but once again, I would just like to include this to be safe so that we're extra precise, and this would get us 2 out of 2. Question 28, we have the polynomial function g of x has a factor of x minus 3, and we have to determine the value of a. And notice here that a is the coefficient of x squared. So for this question, the big idea is we have to know that factors and roots have an opposite relationship. So I think about if I wanted to find the roots of g of x, I would factor this entire expression, and one of the factors is x minus 3, and then I would set each of the factors equal to 0. So if I know one factor is x minus 3, I set it equal to 0, and that tells me that when we solve, x equals 3 is a root. So this is a root of g of x. And now think about, what does it mean for a value of x to be a root? That means when you plug it into the function, you're going to get 0 as an output. So now I would just go ahead and do that. I'm going to plug 3 into g of x, and that means we're replacing every x with a 3. So we have 3 to the third power, plus we have a times 3 squared, minus 5 times 3, and then we tack on the plus 6. And now if we simplify this a bit, now we have 3 to the third power is 27, plus 3 squared is 9, so we have 9 times a, minus 15 plus 6. So now we just combine the numbers. We have 27 minus 15 is 12, and then plus 6 is 18. So g of 3 is going to be equal to, we're going to have 18 plus 9a. And now this part here we could set equal to 0. So we have 18 plus 9a. We set that equal to 0, and now just do the algebra. We do minus 18 on both sides. So now 18 minus 18 cancels, and we have 9a equals negative 18. So we divide both sides by 9, and this is going to tell us here that the value of a is equal to negative 2. Question 29, we want to write a recursive formula for this sequence here. So for this question, there's two very important things we have to know. For one, we have to know what a recursive formula is, and that's when you start out with some terms. So here we're starting out with the first term is 189, and you could start out with 2 terms, 3 terms, or more, but your a sub n term, your general term, is built by the stuff before it. So what I'm thinking about is we're going to have a sub n equals something, and we're going to have an a sub n minus 1 attached here. Sometimes we have an a sub n minus 1 and an a sub n minus 2 term attached here, but in this case here, it's going to be simpler. And then the next thing that we have to know is what type of sequence is this? So let me just draw that a little bit neater. So is this an arithmetic sequence or a geometric sequence? So I noticed to get from one term to the next that we're dividing by 3. So right away, I could see that this is geometric because when you multiply or divide by the same number each time to get to the next term, that's a geometric sequence. But a nicer way of saying divide by 3, we could say that our common ratio, is 1/3, that we're multiplying by 1/3 each time. So now we just put it all together. A1 or A sub 1 is equal to 189, that's our first term. And then our A sub n term, our general term, is 1/3 of the previous term. So the previous term is A sub n minus 1 like this. So this here would get us full credit. Now, before we move on, just be careful. Please don't do something like this. Don't say A sub n equals the first term 189 times 1/3 to the n minus 1. Okay, this is a very, very dangerous bear trap. This would be an explicit formula. Okay, so this would represent the explicit formula for the sequence given above. But once again, they wanted us to give a recursive formula, not an explicit formula. So this is a nice answer, but this would only get us 1 out of 2 points. If we want the full credit, we have to write it in this form here. Question 30, we have to algebraically solve for x, and we're going to round to the nearest thousandth place. So for this one here, we're getting x by itself, and x is in the exponent spot. So I would start here by dividing both sides by 2. So I would divide both sides by 2. 2 divided by 2 just cancels out like this. And now we have e to the 0.49 times x equals 15 divided by 2 is 7.5 or 7.5. So we'll just write it like this. And now we have to think here. Let me just move this over. So what is the opposite of e? So I'm just going to leave a little space here. What is the opposite of e? Because we want e to cancel out. And the opposite of e is natural log. So I'm going to take the natural log of both sides like this. So the natural log of the left side and the natural log of the right side. Because natural log and e cancel out. And now all we're left with 0.49 times x equals natural log of 7.5. So now to solve for x, just divide both sides by 0.49. And the rest is calculator work. So let's just type this in. We're going to press alpha y equals enter to pull up a blank fraction. And we're going to have natural log of 7.5. And we're dividing by 0.49. So that's going in the denominator, 0.49. And then this is the decimal we need. So now we can record our answer. But remember, we're rounding to the nearest thousandths place. So we're going to look 3 digits after the decimal. And over here we have a 2. We look to the right as a 0. So we're rounding down. We could say x is equal to 4.112. And this is our solution to question 30. Question 31, for all values of x for which the expression is defined, we're going to write the expression below in simplest form. So for this question here, we want to simplify this. So we could do this by factoring everything and then canceling common factors. So for the top, we have 4 terms. So we're going to use factoring by grouping. So let's try this out. We're going to take out the greatest common factor here, which is x squared. And then if we divide each thing by x squared, we're going to be left with 2x plus 1. If you want to check to see how we're factoring, you could always distribute in your head, and it should bring you back to the previous line. So now we focus on the next 2 terms here, the minus 18x minus 9. And the goal is to generate a matching 2x plus 1. So this time around, I would take out a minus 9. And now if we divide each of those things by minus 9, we're going to be left with 2x plus 1. So there's our matching 2x plus 1. So we could take that out, and we have 2x plus 1. And now we write the leftovers. We have x squared, and then we're left with minus 9 on the next set of terms here. So we have minus 9 going after. And now I'm looking at this and thinking difference of 2 squares. So I could already see that there's going to be a lot of factoring for this question. And now for the bottom here, we have 3x minus x squared. For that, we could take out a greatest common factor of x. So now we're focusing here on the bottom stuff. So we're over here, and this time around, we're taking out an x, and we would be left with 3 minus x. Okay, so that's just going to transfer all the way across. So we have 3 minus x left here with an x in front like this. So now we could factor this stuff here. So I'll move the highlighted stuff over here to x squared minus 9. So that's what we want to factor next. So for the next line, what we're going to have is now we have 2x plus 1 times difference of 2 squares. We're going to have x minus 3 times x plus 3. Okay, so x squared minus 9 factors very nicely here to x minus 3 times x plus 3. And now we go back here to think of the denominator. We're left with x times 3 minus x. So now we look for matching factors. And notice here, x minus 3, 3 minus x just cancel. No, we have to be very, very careful here, okay? This is a very dangerous bear trap. And it would be so sad if you got this far and then that's where it gets you. What you want to think about for this question, this is a very evil trick here on how they get you. But anytime you have factors that are almost matching, but they're just flipped and there's subtraction between them, this simplifies to -1 as long as a is not equal to b. Because otherwise you get 0 over 0. Okay, so whenever this happens, you're left with -1. And if that didn't make 100% sense as to like why that happens, what you could always do is you could factor out a -1 from, let's say, the bottom, I could always do something like this. I could say 2x plus 1 times x minus 3 times x plus 3. And then I could take out a negative 1 on bottom. I could say x times, and I take out a negative 1. And if I divide each of these things by negative 1, I would have x minus 3 left. Okay, so if you want to just memorize this rule, you could just cancel these factors and replace the canceling factors with the negative 1. Or you could just take this part here. So we'll move the highlighted stuff once more. So we're going to take this, and actually let's not take all of it together. So we'll just take the highlighter stuff. So just this part. And we'll see here that negative 1 times x minus 3 is equal to just 3 minus x. Okay, so if I factor 3 minus x into this form, now everything will just cancel out nicely. And notice here, x minus 3, and we'll not write in highlighter, let's write in pen. So we're going to have x minus 3 is going to cancel out x minus 3. So now let's just write all the leftovers. We're going to be left with, on top, we have 2x plus 1 times x plus 3. And then on bottom, we have negative 1 times x, which is negative x. So we could write our answer like this, but just know we could also move that negative in front of the fraction like this. We could say negative, and then we have 2x plus 1 times x plus 3, and we're dividing by just x like this. Now, one last mention before we move on, that last detail, just in case that's not 100% clear, because that's a sneaky detail for fractions. Just know if you had a fraction like negative 7 over 5, you could write this as 7 over negative 5, or you could write this as negative and then write 7/5 off to the side. So the placement of the negative is pretty flexible when all you have left is multiplication and division. But either way, we could say any one of these is our correct answer, but we'll just circle this one because we wrote that all the way to the right. Question 32, an app design company believes that the proportion of high school students who have purchased apps on their smartphones in the past 3 months is 0.85. And then we have a simulation of 500 samples of 150 students was run based on this proportion, and the results are shown below. And now we have, suppose a sample of 150 students from your high school showed that 88% of the students had purchased apps on their smartphones in the past 3 months. Based on the simulation, would the results from your high school give the app design company reason to believe their assumption is incorrect, and explain? So when I go through questions like this, I think of this famous quote from Abraham Lincoln that goes along the lines of, you give me 6 hours to chop down a tree, and I'm going to spend 4 hours sharpening the axe. So something like this, I would have to reread that last bit a bit more and think about what they're actually asking here, that we're going to use this simulation. And with the results here, with this 88%, give the app design company reason to believe their assumption is incorrect. So we want to determine here, is 88% something that's reasonable based on what we have here? So the idea is to look for, does 88% fall within the confidence interval, which is plus or minus 2 standard deviations from the mean. So if we look here, the mean is at 0.852. Now be mindful that 88% is the same thing as 88 out of 100, which is the same thing as 0.88. Okay, so it helps to turn this into decimal form so that when we look at the confidence interval, we could just see if this number falls in that confidence interval. So now to calculate our confidence interval, we're going to take the average or the mean, so that's 0.852, and we're going to do plus or minus 2 standard deviations, and one standard deviation, they told us, is 0.029. So we have 0.852, and first we'll do plus 2 standard deviations. We have plus 2 times the standard deviation was 0.029, and we close the parenthesis here, and this represents our right endpoint. So this is the end going to the right of our confidence interval. But now I'm going to do minus. So I'm just going to go up to this part here and press enter so that I don't have to retype everything in. And I'm going to go up to the plus, and I'm going to switch it to a minus. So we just switch that to a minus, and now this represents the other end of our confidence interval. So now let's just record the result. We have a confidence interval going from 0.794 up to 0.91. So now think about the question again. We're trying to see here, based on the simulation, would the results from the high school give the app design company reason to believe their assumption is incorrect? Well, the 0.88 is between these two numbers here. So this result here is totally reasonable. So we would just say here, no, that the app design company has no reason to believe their assumption is incorrect because 0.88 is on this confidence interval. Question 33, we have Patricia creates a cubic polynomial function p of x with the leading coefficient of 1, and the zeros of the function are 2, 3, and negative 6, and we have to write an equation for p of x. So for this one here, I'm thinking about what I said before, and that's that roots and factors have an opposite relationship. So if I know that the zeros are x equals 2, we have x equals 3, and we have x equals negative 6, What I'm thinking here is that the factors are opposite. So my factor from x equals 2 would be x minus 2. And then my factor from x equals 3 from that root would be x minus 3. And then my factor from x equals negative 6 would be x plus 6. So I'm just taking the opposite here. And this is going to help us build an equation for p of x. So I have p of x equals, and now I just write everything down. I'm going to have x minus 2 times x minus 3 times x plus 6. Now notice here they didn't tell us to write this in standard form. So I don't actually have to multiply all this out. I could do it, but it's not worth the risk. I'll just leave it like this. Now I know I don't have to add any extra stuff to it because they told us that we have a leading coefficient of 1. So I don't have to actually multiply this stuff by anything else, because when I distribute here, I'm going to have x times x times x is x to the third. So that would be my leading term. And notice my leading coefficient here is 1. So the form I have it in right now is fine. And this would get us credit for the first part. But now for the rest of the credit, we just have to sketch this function on the set of axes below. So I'm just going to type this function p of x into the y equals. So now we press graph here, and notice this is what our curve looks like. And the first thing that jumps out at me is that we have our 3 roots, and they're occurring here once again at negative 6, at 2, and 3. And we have this function is going up, down, and then back up again. Now this phrase here, the fact that we're just sketching this function and we're not graphing it means we don't have to be super precise. But one thing I will be precise with is the location of the roots. Is that notice we have roots here at negative 6. We have a root here at negative 6. We also have a root at x equals 2. So we have a root here at 2, and we have a root here at 3. And then the rest is just drawing this going in the correct direction here. Once again, this function is increasing, then it starts to decrease. It hits the y-axis on the positive side of the y-axis. It hits this root here at 2, goes under the x-axis, and then comes back up. So this is all we would need to put on our sketch here to get full credit. So question 34, we have a public radio station held a fundraiser, and the table below summarizes the donor category and the method of donation. And now this is the information that we need. And the first part of the question is to the nearest thousandth, so that's what we're rounding to. We're going to find the probability that a randomly selected donor was categorized as a supporter, given that the donation was made online. So for this part here, we're once again calculating the probability that someone was categorized as a supporter, given that the donation was made online. That tells us to just focus on this row here, and we want to calculate the probability that we have a supporter in this row. So what I like to do for these questions first is find the totals. So here we have how many supporters. We would just add 400 plus 1200, and that would give us 1600. And then we could add the patrons here. We're doing 672 plus 2016. So this we just do by hand. 2 plus 6 is 8, 7 plus 1 is 8, 6 plus 0 is 6, and then the 2 just carries down like this. And then if I go across, 1200 plus 2016 would give us 3216. And then 400 plus 672 is 1072. And now to find the total here, how many people are there all together? Just add these two numbers, and you have 2 plus 6 is 8. You have 1 plus 7 is also 8, 0 plus 2, and then 1 plus 3 is 4. So this is like our complete total. That'll just make the calculations easier in a moment. So now, once again, we want to find here the probability that someone was categorized as a supporter, given that the donation was made online. So that's this row once again, and there are 1,200 supporters out of how many people are there online altogether? That was 3,216. But now, if we want to use nice notation here, we're calculating the probability that someone is a supporter given that the donation was made online. So this notation here, if we write P parenthesis S with this vertical slash and then O, means probability that someone is a supporter given that they donated online. And that's equal to this value here. So we'll just type this in. We have 1,200 and we're dividing by 3216. So divided by 3,216. And this is the decimal we need. And remember, we're rounding our answer to the nearest thousandth. So we're going to look 3 digits after the decimal. And we look to the right, we have a 1. So we're going to round down here to 0.373. So now for the second part, do these data indicate that being a supporter is independent of donating online? And we have to justify our answer. And remember, for the regions, justify just means you have to show the math to back it up. So I'm thinking of 2 different methods for doing this question. And for one of them, you could just think about the formula. When you want to show 2 events are independent, and in this case, that's being a supporter and donating online, we could use this formula here, the probability of S and O happening. So the probability of someone being a supporter and donating online, we would have to show that it's equal to the probability of someone being a supporter times the probability of somebody donating online. So this method is very nice and it's very formulaic, but I would say here the nicer way of doing this question, because we already did a lot of it in part 1, we found the probability of someone being a supporter given that they donated online. So if we could show here that's the probability of someone being a supporter given that they donated online is just equal to the probability of someone being a supporter, that would show that these two events here are independent. And once again, I think this one is easier because we already did the work in the first part of this question. So what is the probability of somebody being a supporter? Well, we already found all of these totals here. So here's the supporter column, and there are 1,600 supporters. Out of how many people were there in total? In the entire study here, or in the entire data collection, there's 4,288 people. So now we could just type this in here. In moment of truth, we have 1,600, and we're dividing by 4,288. And let's see if we get a matching probability here. And notice here that these do in fact match, so we could say that these events are independent. So now let's record the result here. This is equal to, we have 0.373, and we'll round this one to the nearest thousandth as well, because that's what we did in part 1. And now we just have to comment here. Notice that these probabilities are equal, so these events are independent of each other. Now, before we move on, let's explore the second option here and see that it brings us to the same conclusion. So let's check out the left side first. What is the probability of someone being a supporter and donating online? So we can see here that the supporter column is here and the online row is here. So there are 1,200 people that are supporters that donated online. So that's 1,200 people out of how many were there in total? There was 4,288 people total. So we'll just divide here and see what probability we get. So we get this value here. And now to verify, what is the probability of S? What is the probability of somebody being a supporter? That we could just type in parentheses. That would be 1,600 because there's 1,600 supporters out of there's 4,288 in total. So there's 4,288 in total, and we're going to multiply that by the probability of someone donating online. Well, there are 3,216 people that donated online out of how many total? There were 4,288 people in total. So now we multiply those probabilities together to see what we get, and notice that we get a match here. So because this equation holds true, we could say that these events are independent, that someone being a supporter and donating online are independent of each other. Question 35, we have to algebraically solve the system, and in the system we have the equation of a circle and the equation of a line. So we want to find out what points do they have in common. So for this one here, the most straightforward way to do this, I would say, is by substitution, because the second equation is already solved for y. So we could just plug in for y in that first equation, and that'll get us on the way for finding the solution to the system. So we're going to have x minus 2 squared plus, and I'll leave a space for the y because we're going to substitute. So we have minus 3 squared inside the parentheses equals 20. And remember, we're going to do this by substitution. So we're going to replace y with negative 2x plus 7. So we have negative 2x plus 7. And now notice that our first equation is all in one variable. So now we could actually solve this thing. So just be careful here. Don't do something like this. Don't say x squared plus 4. All right, that's a very dangerous bear trap. Please make sure that you actually expand this and you write this out as x minus 2 times x minus 2. And now for the second part here, this is going to simplify to, we're going to have negative 2x plus 4 squared. So this is going to combine to 4. So if I want to expand this all in one step, I'm going to have negative 2x plus 4 times negative 2x plus 4. Because once again, the line above, this is really negative 2x plus 4 after we combine 7 minus 3. So we have negative 2x plus 4 squared, which expands like this. So now we have this equation here set up. This is all equal to 20. Now we have to actually distribute. So we're going to have x times x is x squared. We have x times negative 2 is negative 2x. Negative 2 times x is negative 2x. And then negative 2 times negative 2 is positive 4. And then we have negative 2x times negative 2x is positive 4x squared. We have negative 2x times 4 is negative 8x. And then we distribute the 4. We've got minus 8x. And we've got plus 16. And this is all equal to 20. So now for this part, we have to combine like terms. So let's think about the like terms here. We have x squared plus 4x squared. That's going to make 5x squared. And then we have negative 2x minus 2x. So that's a lot to keep track of. So let's think about that over here. We have negative 2x minus 2x so far is minus 4x. And then we have minus 8x, which is minus 16x. And when you combine those two, you get minus 20x. So all the x's combine to minus 20x on the left side. And then all that we have left on the left is 4 plus 16, which is 20. And this is all equal to 20. And notice this matches on the right. We have matching constants. So when we subtract 20 in a moment, these terms are just going to cancel out. So now we have 5x squared minus 20x is equal to 0. And to solve for x here, we're just going to factor out the greatest common factor, which is 5x. So we have 5x times, and we're left with x minus 4 after we divide each of those terms by 5x. And now we set this equal to 0. So now set each factor equal to 0. We're going to have 5x equals 0. And that's true when x equals 0. So that's our first root here. And then we have x minus 4 equals 0, which is true when x equals 4. So we have to be careful though. We're not done here. We have to solve for the corresponding y value for each of these x values. So we have the x equals 0 part here, and then we're going to have the x equals 4 part right next to it. So now I would just plug it into that second equation, because notice that it already says y equals. So if we plug into the second equation, we have y equals negative 2 times 0 plus 7 is going to give us y equals 7. So our solution here is going to be the point 0.07, and we'll write that all out at the end. But now for when x is equal to 4, if we plug in 4 for that second equation, we're going to have y equals negative 2 times 4 plus 7, and that's going to simplify to negative 8 plus 7, which is negative 1. So now our solutions, we could just write them out as points here, are going to be the points 0, 7, and then we also have 4, negative 1. So these are the solutions to our system of equations. Question 36, we have a tropical island. There's currently 500 palm trees and 200 flamingos. And then we have, suppose the palm tree population is decreasing at an annual rate of 3% per year, and the flamingo population is growing at a continuous rate of 2% per year. And we have to write two functions, capital P of x and capital F of x, that represent the number of palm trees and flamingos on this island respectively, x years from now. So for this question here, we have to know these two formulas. For the first formula, we're going to need a equals p times 1 plus or minus r to the t power. And this is for annual growth. Okay, so this is a little bit more of a simple formula than the next one. For the stuff in red here, for the flamingo population, we have continuous growth. So we're going to need this formula. We have a equals pe to the rt. So this is continuous growth. So that was a little sneaky detail, is that you have to know both of those formulas. So then think about for the first part here, for the palm trees, we have the population is decreasing. So that means we're going to be going with the minus here. Plus or minus means if we had population growth, we would do 1 plus r. And since the population is decreasing, we're going to go with 1 minus r. So r represents the rate here, and the rate is 3%. So we just have to write 3% as a decimal, which we could find by doing 3 over 100, which is 0.03. And then for the stuff in red, our rate here is 2%. So r equals 2 out of 100, and as a decimal, that's 0.02. So now we could just plug into the formulas, and we'll have here for the stuff in blue, we have the palm tree population as capital P of x is going to be equal to, but here instead of using t, we're going to use x. So now we just plug in. Capital P represents the initial population. So there's right now 500 palm trees, and then we're going to have 1 minus because the population is decreasing at a rate of 3%, which as a decimal is 0.03. And we're raising this up to the x power because this is a function of x. So P of x simplifies nicely to 500 times 1 minus 0.03 is 0.97, and we're raising this up to the x. And now for capital F of x, that's our flamingo function. We have capital F of x equals the initial flamingo population is 200, and then we have e to the power r is 0.02, and then we're multiplying by t, but in this case here, we're going to use x. So we just have to switch letters. For the second part of the question, we have to state the solution to the equation P of x equals F of x. We're rounding to the nearest year, and then we have to interpret the meaning of this value within the given context. So to find out when is P of x equal to F of x, for this part here, we could just use a calculator because notice they just said state the solution. So what we could do here, we just go to the y equals, and we're going to type both of these functions in. We're going to have 500 times, we have 0.97, and that's being raised up to the x. So we press the up arrow here to make an exponent, and we're putting our variable x there. And now we have 200 times e is second natural log, and then we have the power 0.02, and we're multiplying by x. So now we press graph, and notice that we have no graph here. And the reason for that is when we press second graph to go to the table, is notice that the y values are pretty big compared to the y values we have right now. So what I'll do is I'll bump the y maximum up to 600. So that way we could see what's going on. So we do this. And now this is a little bit better, but notice we don't have our point of intersection, which would represent the location of our solution. So we need to extend the graph out a bit. So I'm going to extend it out here to 20 and see if that gives us what we need. So we go out to 20, and now notice we have our point of intersection. If I want to make this graph even nicer, I'll make the x minimum 0, because x represents the number of years that pass by from right now. So we're not going to go back in time. We're just going to be looking forward. So we'll make our x maximum 30 just so we could see a little bit more. And now notice we have a nice point of intersection. So we press second trace number 5, and we go right up to the point of intersection here. and just press enter 3 times. So we have enter, 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 and it gives us the solution we need. So now we just record our answer, p of x equals f of x when x is equal to 18. And we're rounding to 18 because they told us to round to the nearest year. And if we look at the ones place here, we have an 8, and to the right is a 1, so we're rounding down to 18. But now think about, what does this answer mean within the given context of the question? Well, they told us that p of x and f of x represent the population, or the number of palm trees and flamingos, x years from now. So our solution, x equals 18, tells us when the functions are equal, which will tell us how much time has to go by for the population, or the number of palm trees, to be equal to the number of flamingos. So now we move on to part 4, which has our final question, and that question is worth 6 credits. Question 37 has 3 parts, but first up here we have the volume of air in an average lung during breathing could be modeled by the graph below, and we have to use this graph to write an equation for n of t, where n of t is equal to a sine of bt plus c. So for this question here, we have to take it piece by piece, and the first part I like to find here is the midline. That refers to the c value here at the end of the equation. And to identify the midline, you could just imagine the halfway point here in this graph, and that's going to be this location over here. But if that doesn't do the trick, what you could do is just take the average of the maximum and the minimum value, and that'll tell you the midline. But once we know that this is the midline here, we have to find out the exact value. So notice that we're going from 2,000 to 3,000, and we're jumping 1, 2, 3, 4, 5 times. So that means that the y scale is jumping up by 200s. So if I go up 200 twice from 2,000, that brings me up to a height of 2,400. So that would tell me my c value here is 2,400. Now, after I find the midline, the next thing I like to find is the amplitude, which is the coefficient here of the sine function. And on the graph, the amplitude we could find by finding the distance from the midline to the max, or we could find the amplitude by calculating the distance from the midline to the minimum. So if we just counted here, remember the y-axis was jumping up by 200s. So it takes me 2 jumps to get up to the maximum from the midline. So that tells me that my amplitude is 400. And if I wanted a label here, if I go up 400, notice that brings me up to 2,800, which matches my high point here. And if I did 2,400 minus 400, it brings me to my minimum value of this graph, which is 2,000. So that's looking good. Another way of identifying what your amplitude is you could subtract. You could do 2,800 minus 2,000, do the max minus the min, but then you have to divide it by 2, because a common mistake is that when people find the amplitude, they find the distance from the max to the min. But remember, you would have to divide it by 2, because the amplitude is the distance from the midline to either the max or the min. So now the last thing that we have to find to write this equation is the b value, and the b value is the frequency of the graph. And to identify the frequency, I find these equations to be very helpful. So just know these equations here, that f is equal to 2 pi divided by p, where f is frequency and p is period. And I could also say that p is equal to 2 pi divided by f. So sometimes I need the first equation and sometimes I need the second equation. They're both very helpful. So looking at this situation here, we have to know what is the period of the graph. And to identify the period, you want to think about how long does it take the graph to complete one full cycle. And just looking at what they gave us one full cycle, because notice that we start at the midline, we go to the max, back to the midline, then we go to the minimum, and then we go back to the midline like this. If I were to continue drawing this graph, notice that I would be redrawing what they gave us in the beginning. So that tells me that we have one full cycle right here. So now I think about this and say, okay, the period of the graph is equal to 5 because it takes 5 seconds for this graph to complete one full cycle. So now when I want to identify what the frequency is, the frequency is equal to 2 pi divided by the period, which is 5. So that tells me here that my b value is equal to 2 pi over 5. So now we're ready to write our equation. We just plug everything in. We have n of t is equal to, and then our a value is 400. So we have 400 times sine of b was 2 pi over 5. So we have 2 pi over 5 times t, and then plus c, and our c value is 2,400. So now let's verify that our function is good. And to graph this, we have to make sure that we're in radian mode, because when you're graphing trig functions, you have to be in radians. So for this part here, we have 400, and now we have sine of 2 pi over 5. I'll use alpha y equals enter to pull up a blank fraction. And we have 2 pi over 5, and we're multiplying by t here, but we're going to use x because that's our calculator's variable button. And then we're going to write plus 2,400. So now to get the right scale, we have to look at the graph here, and it's going from 0 to 5 in the x direction, even though our function is a function of t. And then in the y direction, we're going up to 6,000. So we go to the window here, and we're going to make our x minimum 0 and our x maximum 5, because that was the scale on the x-axis. And then we look at the y minimum, that's going to go to 0, and the y maximum is going to go up to 6,000. So we press graph here, and notice that the graph that we get matches the graph that they gave us here. And if I want to be really sure, I could type in our midline. Our midline was y equals 2,400. And notice that when we press graph here, that we have the midline of this trig function here. So this function is looking good. So now for the second part of question 37, we have a new function e of t, where e of t is volume in milliliters and t is time in seconds. And this is talking about the same lung, but now it's engaged in exercise. And we have to graph at least one cycle of e of t on the same grid as n of t. Now to graph e of t, we are going to use the calculator, but it does help to know a little bit of theory to make sure that we're using the calculator properly. So I would want to identify here the a, b, and c value. The a value is 2000, that's our amplitude. Our b value is pi, and that's our frequency. And then the c value is 3200, that's our midline. And remember from before, these equations are going to be very helpful. And in this case, we're going to need the second equation. Our period is equal to 2 pi divided by the frequency, and the frequency is pi. So that tells us that we have a period of 2. And how that helps me for this question is I think about the graph. It's going to take 2 seconds for this graph to complete one full cycle. So if I think about the space from 0 to 2, the graph is broken up into 4 sections, and the 4 sections are equal. So if I break up the distance from 0 to 2 into 4 sections, they're going to be counting by 0.5 here. So we have 0.5, we have 1, and we have 1.5. So this is going to be helpful when we have to build our graph. So now let's type in e of t. So we're going to have e of t is equal to, we have 2000, and we have sine of pi t. So sine of, we write second up arrow here for the pi, and then instead of t, we're using x. And then we have plus 3200. So we graph this here, and notice that we have a bunch of cycles here. This is more than one cycle. We have 1, 2, and then it looks like we have half of a cycle. So 2.5 cycles here. So now we have to just graph one full cycle. If we want to graph more, we can, but we only need to graph one. So now think about if we press second graph here and go to the table, notice that this table is not very helpful at all because all of the y values are 3200. But remember what I said before, the period is 2. And what we look at here, if the period is 2 and we break this into 4 sections, we're counting by 0.5. So a nice little trick that we could go with here is we can make a custom table. We could press second window and we could change this from auto over to ask. And now when we do this, we have a custom table, and I could type in the decimal values. So we have 0, but remember I said I was interested in what's going on at 0.5. So I type in 0.5, and that's going to bring me up to 5200. So now I have something other than 3200. And now I write in, we have 1, we have at 1.5, and then we have at 2. And notice what we have here, this gives us our full cycle. We go from the midline to the max, back to the midline, to the minimum, and then back to the midline. So now let's go ahead and plot these points. So we have first 0, 3200 is over here. And then we have 0.5, 5200 is way up here. Okay, so this is just making sure I'm lining this up correctly. That's 0.5, 5200. And then at t equals 1, we're back to the midline over here at 3200. So this is our next significant value. And then at 1.5, we go to our minimum value at 1200. So that's going to be over here. And then at 2, we go back to 3200. So that's going to bring us, let's make sure we line this up properly. That's going to bring us over here. And now all we have to do is connect this with the wave. Now, if we want to verify that all of this information is good here for e of t, so we're looking at e of t over here, we have an amplitude of 2000 and we have a midline of 3200. So we're just using this terminology from before. So notice here, this is our midline. And if we look from 3200 up to 5200, that is an amplitude of 2000 because we would have to add 2000 to get from 3200 up to 5200. And if we look over here at our minimum value at 1200, that would be taking the midline value 3200 and subtracting the amplitude 2000, and that would bring us here. So this is looking good. So now for the last part of this question, how many times during the 5-second interval will n of t equal e of t? So for this, we could just go back to the graph. So now what we want to think about for that last point is how many times did these graphs intersect on this interval here from 0 to 5. And remember, we set the calculator window setting to go from x minimum 0 to x maximum 5. So that's our 5-second interval. So we're looking for the points of intersection. How many of them do we have? We have 1, 2, 3, 4 points of intersection. So how many times? These functions are going to be equal 4 times.